In this lecture, we are going to look at controllers. A controller is used to alter or shape the performance of a system so that it meets the required criteria. To do this, a controller introduces a TF that we can denote as GCS into the system. This TF causes a change of the system dynamics. We can carefully select the TF so as to make the system dynamics meet the required criteria. A controller may, however, also bring about additional and undesirable changes. Therefore, the choice of the controller TF is a compromise between a number of factors. The control configurations that are used are a controller placed in the forward path and a controller placed in the feedback path. In this diagram, we are shown a controller in the forward path. The controller acts on the error signal ES to generate the control action US. The control action is then applied into the process so as to change the output CS towards the reference level. We also note that there is a disturbance DS which adds to the output of the controller before being applied into the process. The TF of the controller is given by US over ES. In this diagram, we are shown a controller in the feedback path. The controller acts on the output CS to generate a control action US. The control action is compared to the error signal to generate an actuator signal UAS. The actuator signal is applied into the process so as to change the output CS in such a way to make it match RS. The TF of the controller is given by US over CS. To assess the effect of a controller on a system, the controller TF is incorporated into the system model. The resulting closed-loop system response is then obtained. After that, reference tracking performance, disturbance rejection performance, and stability are assessed. The effect of the controller on the system is then evaluated by comparing the performance of the compensated system to the performance of the original system. A compensated system is a system in which a controller has been incorporated. For a controller placed in the forward path, the respective expressions for the reference tracking response and the disturbance rejection response are as shown. Once we get the actual expressions, we can be able to determine the transient and steady-state performance parameters of the respective responses. For stability, we notice that the characteristic polynomials of the reference tracking response and the disturbance rejection response are the same. Since stability depends on the characteristic polynomial, it means we can evaluate the stability of both the responses simultaneously. Let's now discuss the basic forms of common control laws. We shall begin with proportional control. In proportional control, the control action is proportional to the error. Mathematically, UT equals Kp by ET. Kp is a constant. UT is the control action and ET is the error. In Laplace domain, US equals Kp by ES. Therefore, the TF of the controller is Kp. Kp is referred to as the proportional gain constant, and it tells the amount of proportional control. Integral control. In integral control, the control action is proportional to the integral of the error. Mathematically, ut equals ki by the integral from 0 to t of et with respect to time. In Laplace domain, us equals ki over s by es. Therefore, the TF of the controller is ki over s. Ki is referred to as the integral gain. It tells the amount of integral control. In derivative control, the control action is proportional to the first derivative of the error. Mathematically, ut equals kd by det dt. In Laplace domain, us equals kds by es. Therefore, the TF of the controller is kds. Kd is referred to as the derivative gain. It tells the amount of derivative control. Each of these controllers that we've looked at has respective effects on the system response. Find out what these effects are and verify them by analyzing and comparing reference tracking and disturbance rejection for various control cases. The work is not meant to be submitted, but it is for you to gain more knowledge on these control laws. To exploit the advantages of the individual control laws, the basic control laws are implemented combined. The useful combinations that we can make are proportional plus integral, proportional plus derivative, and proportional plus integral plus derivative. It is important to note that in these composite controllers, proportional control is always a component. Also, it is important to note that derivative control cannot be used on its own because it does not respond when the error is constant. For proportional plus integral control, known as PI control, the TF of the controller is equal to Kp plus Ki over S. In standard form, the TF can be expressed as Kp open bracket 1 plus Ki over Kps close bracket. This is equivalent to Kp open bracket 1 plus 1 over Tis close bracket, where Ti equals Kp over Ki. Ti is known as the integral action time. I will task you to go and find out why it is called the integral action time. For proportional plus derivative control, known as PD control, the TF of the controller equals Kp plus Kds. In standard form, the TF equals Kp open bracket 1 plus Kds over Kp close bracket. This is equivalent to Kp open bracket 1 plus Tds close bracket, where Td equals Kd over Kp. Td is known as the derivative action time. Again, I will task you to go and find out why it is called the derivative action time. For proportional plus integral plus derivative control, known as PID control, the controller TF equals Kp plus Ki over S plus Kds. In standard form, this TF is equal to Kp open bracket 1 plus Ki over Kps plus Kds over Kp close bracket. This is equivalent to Kp open bracket 1 plus 1 over Tis plus Tds close bracket. Let's illustrate a composite controller using the system given here. The controller is in the forward path and is represented by the TFGCS. The controller has three components: a proportional controller, a derivative controller, and an integral controller. The outputs of the controller components are added together to give the overall control action US. The respective amounts of the proportional control, the derivative control, and the integral control is determined by Kp, Kd, and Ki. Let's have a look at two-step control. In two-step control, the control element processes the input error signal to become a two-level output signal, where the level depends on whether the actual process variable is below or above the set reference level. As an example, in a refrigerator, we have a thermostatic switch. The switch turns on the compressor of the refrigerator when the temperature is above some threshold value, and it turns off the compressor when the temperature is below the threshold value. So therefore, this switch gives two possible states: either the compressor is running or the compressor is not running, and the state depends on the relationship between the temperature in the refrigerator and the set temperature on the thermostatic knob. We shall have a look at a couple of examples. In the first example, we have a PD controller used in cascade with a process that has a TF as given to give a unit feedback configuration. We want to obtain expressions for the damping ratio and the natural frequency after the controller has been introduced. The TF of the controller is equal to Kp plus Kds, which is the general expression for the TF of a PD controller. The closed loop TF of the resulting system is equal to GCS GPS over 1 plus GCS GPS. This works out to Kp plus Kds over S squared plus in brackets B plus Kds plus in brackets A plus Kp. The response is observed to be the response of a second order system. By inspection, the undamped natural frequency omega n equals the square root of A plus Kp, and the damping ratio zeta equals B plus Kd over 2 by square root of A plus Kp. If we're given the values of A and B in the TF, and we wanted the undamped natural frequency and the damping ratio to be certain values, we're going to be able to work out the values of Kp and Kd, and therefore the TF of the controller. In the second example, we are given a diagram that shows the arrangements of components in a liquid level process control system. We are also given the values of the parameters of the components that make up the system. We are required to find the values of Ti and zeta when we're given omega n. We're also required to find the expression for the time response of the system when there's a step change in the reference input. This is the block diagram that represents the system. The tank, which is the process, is a first order system with the TF as shown. The actuator is a control valve with the TF as shown. The controller is a PI controller with the TF as shown. The feedback path is made up of a pressure transducer with the TF as shown. The closed loop TF of the system is worked out and it gives the expression that is shown on the slide. The TF that we obtain is a TF of a second order system. We identify that 1 over omega n squared equals ATI over Kp Kv H1. If we make substitutions for known quantities, we obtain Ti is equal to 5 seconds. Also, we identify that 2 zeta over omega n equals 1 over Kp Kv Rf H1 plus 1. We make substitutions for known quantities and obtain the damping ratio as being equal to 0.417. To obtain an expression for the time response of the system, we make substitutions for all known quantities in the expression of the TF. We then equate the TF to HAS over HDS. HAS is the output of the system and HDS is the reference input of the system, which we are told is a step input. We then perform inverse Laplace transformation to obtain the time response expression in time domain. We obtain the expression shown. The expression shows that the response is decaying oscillations. We go into controller design. Controller design is the selection of a TF of the controller to make the system meet the required specifications. Specifications are based on reference tracking, disturbance rejection, and stability. For PID controllers, the design is selection of the PID terms. The steps that can be followed when designing a controller are: 1. Discover the strengths and weaknesses of the current system. This step will give you the specifications that are required to be met by the system. 2. Decide on the type of the controller that is required to meet the specifications. This is basically selecting between P, PI, PD, and PID controllers. 3. Select values for the control terms. If the process module is not known, you use manual try and error means. If the process module is known, you compare the compensated TF to the required TF to obtain the values of the terms. If the desired positions of the closed loop poles are known, you select the pole positions, and this is known as pole placement. The positions of the poles will give you the values of the control terms. We illustrate the design process using a furnace temperature control system. Shown is the arrangements of the components in the system. We have a furnace, we have a thermocouple to measure temperature, a signal conditioner, a gas solenoid to control the gas flow rate to the gasifier, an amplifier which acts as a proportional controller, and a potentiometer that allows the reference temperature to be input into the system. Thus, the block diagram to represent the system. K1, K3, K4, K5, and K6 are given by the components selected. K1 comes from the input transducer. K3 and K4 come from the actuators, solenoids, and the valve. K5 and K6 come from the thermocouple and the signal conditioning circuitry. K2 is selected to make the system meet the required specifications. Here are some guidelines that are used in choosing controllers when designing certain types of control systems. You can have a further look on these guidelines and then exploit them in the design of control systems that may have similar features. Here is the tutorial exercise for you to do and check if you have understood the concepts that we have covered so far. Please attempt these questions and upload these responses via the Google Classroom.